Hello, this is part of the Controlled Environment Plant Production Engineering / Technology Education modules that were developed and presented by The Ohio State University, Rutgers University, and the University of Arizona, with support from the USDA NIFA program. This module is titled Alternative Energy and Resource Use and is presented to you by A.J. Both at Rutgers University and Murat Kassira at the University of Arizona. The learning objective for this module are that by the end, you should be able to identify alternative energy sources for greenhouse heating and electricity consumption, and you should be able to better assess whether a particular energy use strategy is appropriate for the application you are considering. Additional resources include several websites with good information, as well as books, Greenhouse Engineering, Energy Conservation for Commercial Greenhouses, Greenhouses by Joe Hannon, Greenhouse Operation and Management by Paul Nelson, the Ball Red Book edited by Chris Bates, the National Greenhouse Manufacturers Association, as well as the American Association for Agriculture and Biological Engineers, have developed a variety of standards that I think might be useful for you to review related to this module. There are several alternative energy sources that greenhouse operations can or are using, mostly because in recent years energy prices have gone up considerably, so growers are always looking at alternative ways to save energy and to reduce their fuel bills. So I have a list here of some of the more typical sources, such as solar, wind, and geothermal, and I'm going to go through each of them, or most of them, to give you some additional information about how you might apply these alternative energy sources for a particular greenhouse operation. The first one I show you may be a little bit counterintuitive. These are PV panels or photovoltaic panels installed directly on top of the greenhouse roof. Typically we design greenhouses for maximum light transmission. So by installing these opaque photovoltaic panels on the south-facing sections of the roof, we reduce the overall light transmission into the greenhouse. However, if you're trying to grow a crop that does not require as much light, you might be able to apply this strategy and in addition to letting light into your greenhouse, also generate electricity from the photovoltaic panels on your greenhouse roof. So again, it may not be a system that is useful for all greenhouse operations, but under some conditions, when you don't mind some light reduction, this may be something to consider. If you look at the image inside the greenhouse, you see these very clear shadow bands occurring, so that may be another concern for a particular crop. The opaque panels don't let any light through and create these shadow bands inside the greenhouse. A development that is new and is not yet widely available, that is very interesting, tries to overcome this issue of blocking light when you install photovoltaic panels on the south-facing roof of greenhouses. This is a system that is being tested at the moment that allows part of the light to go through, the light that is used for photosynthesis, which is very similar to visible light, but it intercepts the heat radiation associated with solar radiation and converts that heat radiation into electricity. So you can install presumably a system like this on your south-facing wall, block little, if anything at all, of the photosynthetically active radiation, so plants can still grow as if they were exposed to regular sunlight, but then the heat component of the sunlight is captured and converted into electricity. So we'll see if this becomes more widely available and if it becomes economical to use a system like this. Along those lines, and a lot more low-tech, is also a new development, and I believe is only available in Europe at this moment, is plastic film that is developed with a particular with particular constituents that shift some of the light in the solar spectrum, particularly in this case UV radiation, from the UV component into the visible component. So the UV component is typically not used by plants for photosynthesis, and by shifting that light into the visible light or in the photosynthetically active radiation part of the spectrum, we can increase that quantity of light that plants then can use to grow and develop. So we use this film to modify the spectral qualities of sunlight to try to boost plant productivity. Wind is obviously another energy source that greenhouse operators can use, and here you see an installation of a wind turbine near a larger greenhouse operation. Obviously you need to be in a location where there are sufficient wind conditions to make this profitable, but it is certainly an option for greenhouse operators, and as the economics are becoming more and more attractive, I think we will see more greenhouses install wind generators to help provide electricity for the various components in the greenhouse. You can also use ground source heat pumps to collect energy or to remove energy from the greenhouse, depending on the time of year. We make use of the fact that the ground temperature just a few feet down below the surface is relatively constant throughout the year. And so in the wintertime, that ground temperature is typically warmer than our outside air, and we can extract heat from that ground and bring it into the greenhouse, use a heat exchanger, convert it into hot water that we can then use to heat the greenhouse, for example. And in the summertime, when the ground temperature is cooler than the outside air, we can remove, using the same system, we can remove excess heat energy from the greenhouse and dump it into the ground near the greenhouse operation. So this is an interesting design that I think could be very useful and energy efficient for many greenhouse operations. And typically we recommend that growers install a backup system in the form of a large insulated water tank, sort of a reservoir where they can store excess heat energy to make the overall efficiency of a system like this as high as possible. So using a ground source heat pump system in addition or amended with an insulated water tank is typically a very efficient way of using energy in your greenhouse operation. An example of ground temperatures throughout the United States is shown in this slide, where for a depth of 30 to 35 feet, you can see what the temperatures are throughout the 48 states. Keep in mind that you don't have to go typically that deep to get to that constant temperature. So ground source heating systems do not have to be installed 30 to 45 feet deep. Typically, the ground temperature is pretty stable when you go 3 or 4 feet down already. So you may be able to install a system relatively shallow, and you don't have to go as deep as is shown in this image. A lot of growers have been looking into biomass as an alternative fuel source for heating their greenhouses, and wood is a very typical and useful biomass source that we can use. And here you see an installation of such a system. Shredded wood has been delivered on site and dumped in large piles with various conveyor systems. That shredded wood is then brought to the biomass heating system. That biomass heating system converts that biomass into hot water, and the hot water can then be used to heat the greenhouse. And typically, and as is done in this case, we install an insulated water tank with a system like this to increase the overall efficiency. We do that by running the heating system at its maximum efficiency as much of the time as possible, and then when we have excess energy, that we produce with the heating system, we store it into the insulated water tank for later use. So by incorporating this tank, this storage mechanism with this biomass heating system, we increase the overall efficiency of our heating system. We can also burn pellets. Here you see an installation at a greenhouse site where large silos are used. You see a truck delivering wood pellets that are then stored in these silos, and then from the silo the wood pellets are augered to a large biomass boiler, which you see in the next image here. So you see the white pipes on the top right hand side of the image delivering the wood pellets into an auger system, a hopper system, that then delivers a certain quantity of those pellets into the combustion chamber, and then the fire heats the pipes, the plumbing surrounding the combustion chamber to generate hot water that we then pump throughout the greenhouse. You can also see that the exhaust of this particular boiler is connected to an extractor system that we use to remove any particulate matter that may be coming out of the combustion process before the exhaust gases are then released to the outside environment. So you may have some additional components of a heating system that are necessary to get the right permits to operate a system at a greenhouse site, but you can use a otherwise waste product very effectively for your heating system. You don't have to go to a very large heating system. Here you see an example of a relatively small wood burning system. It uses waste wood. It's a small combustion chamber that is again surrounded by heating pipes or water pipes. So a grower loads a load of wood inside this wood stove, and then a pump is pumping water through the pipes that then can be directed towards the greenhouse for heating the greenhouse. These systems can be very efficient and very effective. One of the challenges is often that you need to continuously stack wood, especially during the winter time when there's a large heat requirement in your greenhouse operation. So you may have to get up in the middle of the night to restack this system. They do sell larger systems that allow for entire pallets stacked with wood to be driven into the combustion chamber all at once. And if you have a larger greenhouse operation, and perhaps if you want to prevent having to get up in the middle of the night to restack your stove, that particular design may be more preferable, because you could stack or pre-stack pallets with wood, and then when needed you just use a forklift to drive an entire pallet right into a stove like this. We can also use different biomass sources other than wood, and here you see examples on the upper left hand side of switchgrass, or on the upper right hand side of miscanthus, two large growing grass varieties that can be used and harvested. We can process the material much like we harvest hay or straw with large bales, and then we could either burn those bales directly, or we could process that material into pellets, for example, that we can then use in our heating system. So in addition to wood, there are also these grasses that we can use to provide an energy source for our heating system. If you are located near an industrial site, such as a power plant or a large industrial manufacturer, they may have additional heat that they're trying to remove from their system. In the power plant, for example, they try to cool down their power generation system, and typically that is done in large cooling towers, as you see in the background here. But we could also use that water that needs to be cooled as the heating source for our greenhouses. So you need to run a pipe from the power plant, in this case, to the greenhouse operation, and then use heat exchangers to extract that heat and help heat your greenhouse facility. This could be a relatively inexpensive form of heat because the industrial processes typically expel that heat to the outside environment. But you need to be cognizant of the fact that these processes, such as power plants and industrial manufacturers, typically need downtime for repairs or maintenance. And during those periods of time, you need to have a backup method of providing you with energy for your greenhouse system. Another alternative energy system is a combined heat and power system where you generate electricity by combusting the fuel source, and then you can use a heat exchanger in the exhaust or the stack system to try to capture the waste heat and use that waste heat to help heat your greenhouse environment. So you're using a generator to generate electricity, and you capture as much as possible any waste heat from the combustion process to try to increase the overall efficiency, conversion efficiency of converting that fuel into both electricity as well as heat. So it could be a very attractive form of generating both power and heat at your facility. It is really helpful when you have a facility like this if you have an arrangement with your local power company that allows you to dump any excess electricity into the power grid. And hopefully you can make an arrangement that provides you some extra income from doing that. If you do that, then these systems might be economical depending on the size of the greenhouse and depending on the type of conversion system you're trying to use. This particular example shows you a microturbine that combusts landfill gas, which otherwise is a waste product, and generates electricity to run the supplemental lighting system on site. Any excess electricity is being sold back to the local power company, and then the waste heat is used to help heat the greenhouse in the wintertime. Here you see a schematic of how that system works. We have a compressor that sucks in outside air and compresses it, increases the density. That compressed air is run through a recuperator, which is a heat exchanger that extracts some of the energy, the heat energy from the exhaust gases, and heats up the inlet air, the compressed heat up air. Then that compressed and heated air goes into the combustion chamber where the fuel is introduced. It could be natural gas, it could be landfill gas. And then the force of the combustion process drives the turbine. And the turbine is connected to a shaft that runs both the compressor as well as converts the rotational energy through a gearbox into a generator that then generates electricity. The exhaust gases produced by the combustion process are collected after they drive the turbine, are ran through the recuperator to try to preheat the compressed incoming air, and then run through a second heat exchanger to heat up, for example, hot water that you can then use to help heat a greenhouse operation before the remaining exhaust gases are then expelled to the outside environment. So this is a very simplistic picture of how a combined heat and power system might work. In this case, the example is for a microturbine that uses the Brayton cycle as a process of generating both electricity and heat. To show you the potential advantages of using these combined heat and power systems compared to conventional systems, I have this little graphic that shows on the left-hand side that for a conventional system where you buy in electricity from the local grid and you have your own individual boiler system to generate heat, you need 154 energy units to generate 75 useful energy units on your site. Whereas on the right-hand side of the image, you see that for a combined heat and power system where you have one unit on site that generates both electricity and heat, for every 100 units of energy that you put in, you generate the same 75 units of energy coming out. So the overall efficiency of the combined heat and power system is much higher than the overall efficiency of going the conventional way, where you buy your power from the power grid and you have your own individual boiler. Now, of course, it depends on where you are and what power company you're dealing with and how the power is generated. These numbers are ballpark numbers, general numbers, but nevertheless, it is typically a lot more efficient to go with a combined heat and power system than with the conventional system where you use power bought from the grid, as well as having your own boiler generating heat energy. There's a new class of boiler technology that I think is very interesting and it typically generates much higher conversion efficiencies than conventional boiler systems. They include the condensing boilers. Think about the combustion process. The combustion process generates typically, if it works well, carbon dioxide as well as water vapor. And it requires energy to generate that water vapor. And that energy is typically lost when we expel the combustion gases to the outside environment. So what this condensing boiler does is it condenses the water vapor that was generated by the combustion process. It condenses it back down to water and extracts, because that process of condensation creates energy, it extracts that energy and uses it typically to preheat the water that is being introduced into the boiler system before it actually is heated by the combustion process. So by condensing that water vapor in the combustion stream, we are able to significantly increase the overall efficiency of the combustion process, and of course that helps save energy. So these boilers are typically low mass. That means that they don't weigh a lot. They are typically have a small footprint. They can be operated almost instantaneously. That means they don't have to run continuously at some low rate to try to have heat available when needed. They typically have a lot less maintenance than larger boiler systems, and they can be used in retrofit installations where you still have your larger boiler system, but you use these condensing boilers sort of as a first stage or a backup system or a boosting system, and then as a result you're able to still benefit from the increased efficiency that these condensing boilers provide. So I think this is something that you should look into if you're considering either upgrading or installing a new boiler system. Growers have also tried to use fuel sources in the same boiler systems or heating systems depending on availability and price. And here you see an example of a boiler that is able to combust either natural gas or fuel oil. And this particular grower uses a system like this to try to reduce the overall price depending on the market price as well as the availability of these two different fuel sources. So if you have an option to do this, you can try to buy or contract for energy supply during times of the year when the prices are lower. And then in the case of fuel oil, you can store some of that fuel oil on site. And then during the winter time, you can decide, depending on the price, for example, of natural gas, whether it makes more sense to continue to combust natural gas or switch to the fuel oil that you bought, for example, during the summertime at a low price. So these strategies may allow you to save energy depending on whether you have a boiler system that is able to accept different fuel sources. Research has been going on in different locations looking at strategies to use greenhouses to actually generate energy, and here you see two examples. On the left-hand side you see the so-called LCAS, or electricity greenhouse, that is trying to generate electricity using solar collectors. So the south-facing roof sections are curved, and are curved so that some of the light is being directed to a single focal point. The glass on the south curved face is also coated so that it allows radiation that is used by plants for photosynthesis to go through, but the heat radiation component is being reflected and directed then to this focal point. And then at this focal point you could put a solar collector, either collecting and converting the solar energy into electricity, or perhaps converting that energy into hot water or another hot liquid, or maybe perhaps a hot gas that can then be used for heating purposes or electricity generating purposes. On the right hand side you see a similar approach, but a little different design. Now the south facing greenhouse roof section is outfitted with a Fresnel lens. That lens is a very thin lens. It's similar to the lens that is used on lighthouses, that is really concentrating the light from a light bulb into a very focused beam. You do the same thing with these Fresnel lenses on flat surfaces. You concentrate that light, that parallel beam that is coming from the sun, into a focal point inside the greenhouse. And if you put again a solar collector at that focal point, you can generate either heat or electricity depending on the system that you have installed. So again, these are systems that are not yet available for commercial greenhouses. These are ideas that are being developed and worked out in an attempt to try to use greenhouse systems not only to grow plants but also to help generate electricity, either for on-site purposes or perhaps even for off-site uses. Greenhouses can also be used to grow biofuels or biomass, and here you see an example of a greenhouse equipped with an algae growing system that then the algae can be harvested and lipids can be extracted that then can be used to be processed into a biofuel. Whether this is an economical approach is a different issue, but obviously greenhouses provide a nice environment for this particular growing system, and who knows, maybe in the future when energy prices continue to rise, we will see more greenhouse operations being outfitted with these kind of growing systems to help produce fuel sources that we need not only to operate a greenhouse but perhaps for other applications as well. In warmer climates, people have designed new systems that are able to generate electricity and or generate water, or produce water. So here you see an example of what is called the Seawater Greenhouse, where cold water is extracted from deep locations in the sea or in the ocean, and that cold water is then used in a condenser system to condense water from a hot and moist air stream. And if you do the condensation process properly, you can end up with clean water that you can then use for example, for irrigation, or if the system is large enough, you could also use that water for drinking water. So the design works by running warmer surface water through evaporative cooling pads, both on the inlet and on the outlet side of a greenhouse. You obviously bring in very warm air from a tropical or a desert environment inside the greenhouse that is typically relatively dry. You use the evaporative cooling pads to moisten that air and to cool that air to provide a better growing environment for the crops inside. And then before the air exits the greenhouse, you run it through another evaporative cooling pad to increase the humidity again. And then you run it through this condenser system with the cold water that you collected from a deeper location in the ocean or in the sea to generate then your fresh water that you can use for irrigation or for other purposes. So you see on the lower left hand side an artist's rendition on how this system works, a heliostat with mirrors collecting solar energy, generating a lot of heat energy in a single focal point that is then used to run a turbine to generate electricity that drives this whole system. and then the greenhouses next to it working on the process I just described, growing crops and also extracting moisture from the air to provide enough irrigation water for the crop. On the lower right hand side you see an example of a trial installation in Australia. I think there's also a few installations already in Middle Eastern countries using this concept. Another alternative design are these large solar updraft systems. Think about very tall towers, perhaps as much as tall as a kilometer or 3,000 feet or so. And at the base of these towers we design and install large greenhouse operations. So as this tower generates this very strong updraft, because it's located in a warm environment where there's lots of sunshine, the air inside the greenhouse will heat up and will through the tower principle, the stack effect, the chimney effect will generate this strong airflow. If we put turbines at the base of these towers, we can then use those turbines to generate energy. And you can see here a design where, a prototype design where a large area of greenhouses was used to generate all this airflow movement that then resulted in turbines generating electricity at this site. You can also see on the right hand side that in addition to using that hot air that's being generated inside the greenhouses to run turbines, you can also put water bags on the floor of those greenhouses to increase the absorption of solar radiation. So during the day those water bags will absorb heat energy, and then at night when the sun is down that heat energy will be slowly released inside the greenhouse. So you may be able to use this principle to heat greenhouses, especially in areas where the night temperature doesn't get too cold. We'd like to acknowledge the funding that was received for this effort by the USDA NIFA program.